Right. So in today's session, we will discuss about a transformer or a practical transformer on no load. Two topics we will discuss today. One is practical transformer on no load condition, and the another one is practical transformer on load. Okay, no load means what? There is no load under that is a on practical transformer. If you are not connecting any load, then we are calling it as a transformer operation on no load condition. So this is a diagram which is nothing but the transformer, right? This is transformer core. This is primary winding. This is the secondary winding. Always to the primary winding we will connect the supply mains. Always to the secondary winding we will connect the load. Okay. See here on the secondary terminals, since I want to analyze the transformer during the no load condition, I have not connected any load onto the secondary terminals of the transformer. That is why the reason we are calling it as a operation of the transformer or operation of practical transformer on no load. I have not connected any load onto the secondary terminals of the transformer. Okay. And as it is, the primary winding is connected with the supply voltage, and that supply voltage, input supply voltage, which is called as V1. So here V1, which represents the input supply voltage which we are applying across the primary winding of the practical transformer. Okay. So whenever you apply the V1 voltage to the primary winding, it causes some current to flow through the primary winding, and this current what is called as I naught. Here I naught, which represents the amount of current which flowing through the primary winding during the no load condition. Why? Because here I have not connected any load on the secondary terminals of the transformer. Whatever the current which the primary it is carrying, and that current what we are calling it is a no load primary current. This is the current which carrying in the primary winding of the transformer, and during the no load condition it is flowing, and it is by the reason the current, this current what we are calling it as no load primary current. Okay. So this current which is denoted with I naught. Okay. So primary winding which is connected with the supply voltage of V1, which in cause to flow the current of I naught through the primary winding of the transformer. Okay. This current which produces some working flux in the transformer. Whenever current is flowing through the winding, then immediately what will happen? Flux will produces, right? So this no load current which flowing through the primary winding in turn produce the magnetic flux in the transformer core. That magnetic flux which is shown here with the helping of the dotted line. This dotted line which represents, I'm just moving the cursor, you can go through that. So this dotted line which represents the working flux are simply called as flux produced. Okay, that flux which is denoted with phi. So whenever the flux, this what is the type of voltage which we are giving as input for the primary winding? It is a sinusoidal voltage. Single phase AC supply we applied. So sinusoidal voltage which in turn produce the sinusoidal current in the respective winding. This sinusoidal current flowing through the primary winding which in turn produce the sinusoidal flux in the transformer core. So when alternating flux, this is an alternating flux, right? Alternating voltage you have given, alternating current will flow through the primary winding, which in turn produce the alternating flux in the transformer. This alternating flux which crosses by the primary winding of the given transformer and which will induce an EMF, thus induced EMF which is known as E1, which which here are denoted with E1, which denotes the amount of primary induced voltage during the no load condition, or we can say that this E1 is nothing but the amount of EMF induced in the transformer of the primary. Okay. So the same magnetic flux which is also crossed by the secondary windings or secondary number of turns, which in turn produces some amount of EMF, and that EMF produced which is denoted here with E2. This E2 is nothing but the amount of induced voltage in the secondary winding. Okay. Since we have not connected any load on the secondary terminals, so there isn't any current to flow through the load terminals, and therefore current supplied by the secondary I2 is equal to 0. What will be the current during the no load condition? Since we have not connected any load on the secondary winding, there will be no current supplied by the secondary terminals of the transformer, and which in turn the current I2 supplied to the load is equal to 0 since it is a open circuited. Okay. So what is the current only flowing during the no load condition is nothing but this I0. Why is I0 which is flowing even the open circuit placed on the transformer? This I0 is the current which is responsible even there is a no load taking place in the transformer, even there is a no load in the transformer, there are some losses which going to be taking place in the transformer. And what are those losses? Even there is a no load, there will be a core loss. ನಮ್ಮ ಟ್ರಾನ್ಸ್ಫಾರ್ಮರ್ ಅಲ್ಲಿ ಏನು ಲೋಡ್ ಇಲ್ಲ ಅಂತಂದ್ರೆ ಕೂಡ ನಮಗೆ ಟ್ರಾನ್ಸ್ಫಾರ್ಮರ್ ಅಲ್ಲಿ ನೋ ಲೋಡ್ ಲಾಸಸ್ ಇರ್ತವೆ ನಮಗೆ. ಸೊ ವಾಟ್ ಆರ್ ದ ನೋ ಲೋಡ್ ಲಾಸಸ್ ವಿಚ್ ಟೇಕಿಂಗ್ ಪ್ಲೇಸ್ ಇನ್ ದ ಟ್ರಾನ್ಸ್ಫಾರ್ಮರ್? ಒನ್ ಇಸ್ ಕೋರ್ ಲಾಸಸ್ and the another one is no load copper losses. Again I am repeating, even on the no load condition of the transformer, there will be some amount of power losses taking place in the transformer, and that power loss which are nothing but what? Core losses, that is hysteresis and eddy current, both will called as a core losses. And the one more power loss taking place in the transformer, and that power loss what is nothing but no load primary copper loss. Okay, so in order to supply this amount of power losses in the transformer, the primary winding of the transformer which takes a small magnitude of current, and that current what we are calling it as I0. I0 is nothing but the no load primary component of current. Okay, so here this is the schematic diagram explanation. Hello, this is schematic diagram, and this diagram which explains you the phasor diagram of the transformer during the no load condition. Coming to this phasor diagram, first let us represent the working flux as a reference phase we will take. So this phi which is drawn horizontally, which represents the working flux in the transformer. Always the working flux which lag behind the supply voltage by 90 degrees. So the V1 phase which we are going to get like this. V1 phase, this vertical line, if the V1 voltage means always to this one 90 degrees lagging the working flux we will have. So this horizontal line which represents the working flux phi. Okay, always the working flux phi which lag behind the supply voltage by 90 degrees. So with respect to V1, this phi phase is having 90 degrees out of phase. Okay, next whatever this no load current I0 is there, this I0 is again split into the two currents. One is magnetizing component of current which is responsible for the production of magnetic flux in the transformer, and the another one is working component of current. Okay, so magnetizing component of current which is denoted with I mu. This I mu here which represents magnetizing component of current. This magnetizing component of current which is in phase with the working flux. Okay, that's why this is the magnetic flux means in the same direction the magnetizing component of current will be there, and that magnetizing component of current which is denoted with I mu. Next another current which is nothing but a working component of current, and this working component of current which always in 90 degrees to the magnetizing component of current. So in this direction now it is in the phase of V1 it is going to be. So vector addition of this working component of current and magnetizing component of current which in result gives the no load current I0. This I0 is nothing but vector addition of IW and as well as I mu. So this I0 current which is equal to what? Whatever the no load current which primary winding carrying, that is equivalent to the vector sum of I mu and as well as IW. Okay, I will just unmute ma. If you have any doubt you can ask me. Okay, so just now we discussed that I0 current which is nothing but splitted into the two currents which is nothing but magnetizing component of current, and the another current is working component of current, and the vector sum of this working component of current and the magnetizing component of current which results in gives the no load current I0, and this current is nothing but which is carried by the transformer during the no load condition. Okay, so from this vector diagram we can denote the value of phi naught. Phi naught is nothing but no load power factor angle. This is an angle between the working component of current and as well as I naught. So this is I naught vector, right? So with respect to this, IW is how much angle which it is having. This angle which denotes phi naught. This phi naught which is nothing but called as no load power factor angle. Okay. So from this vector diagram, what is IW is equal to, which we can write, if this is phi naught means take cos phi naught, and if we calculate IW, then IW is equal to what we will get, I naught into cos phi naught, or simply we can say that cos phi naught, if you take from the vector diagram, simply it is IW divided by I naught. I naught is a hypotenuse and IW is nothing but this vector, right or not? If you take the cos phi naught, this is a descent side and this is hypotenuse, so you will get a IW divided by I naught. So IW is equal to I naught into cos pi naught we will get. So that is what which I have written here. IW is equal to I naught into cos pi naught. In a similar manner, if you write an equation for I mu, what we will get? This is a phi naught. And if you write an equation for I mu, what we will get? This I mu is equal to I naught into sin pi naught we will get. This is the same vector length which this vector length is having. So if you take the sin pi naught here, what we will get? Adjacent, sorry, opposite side will be the I mu. This length is equal to I mu divided by hypotenuse, and that is nothing but I naught. So sin phi naught, which if you take that I mu divided by I naught, we will get. So therefore, the value of magnetizing component of current, which is equal to what we will get, I naught into sin phi naught. And from the vector diagram, as we already discussed, that I naught is equal to the vector addition of I mu and as well as IW. So value of I naught square is equal to IW square plus I mu square we will get. So if you want to get I naught value, that is exactly equal to square root of IW square plus I mu square we will get. Okay. And if you want to calculate the value of power input during this no load condition, from this diagram it will be very clear. I wanted to calculate what is the amount of power input given to this. If I want to calculate that, what this value which is going to be equals to, it is equivalent to V1 into I naught into cos pi naught. So we usually in the case of AC circuit, the power is calculated by VI cos pi, right? So I wanted to calculate power input to the transformer. What is the input voltage which I am giving here? V1. And what is the input current? Here it is I naught. And what is the no load power factor? Cos pi naught. So the value of input power which I can calculate by V1 into I naught into cos pi naught, that is equal to Wi. That is equal to Wi. So as we just discussed that during the no load condition, the total power which the transformer is taking, it is only to supply the no load power losses taking place in the transformer. So during the no load condition, what the losses which is taking place in the transformer? Iron loss, and as a small amount of copper loss which is taking place. So if you neglect that amount of no load copper losses, the total power input during the no load condition, or the total power which transformer taking during the no load condition, it is only to supply the iron losses taking place in the transformer. So therefore, from the no load diagram, we can calculate the value of total power input to the transformer W0. It is only to supply the iron losses taking place in the transformer. So that the W0 value which we can calculate by V1 into I naught into cos pi naught, that is equal to Wi. In this condition, this is equal to Wi whenever we taken the assumption that there is a negligible amount of no load copper loss taking place in the transformer. Okay, provided that assumption only, this W0 which is going to be equals to Wi in the case of no load condition. Okay, so this is about the operation of the transformer during the no load condition. Okay, now we will go to the next topic, that is the transformer operation during the load condition. Okay, if you have any doubt, you can ask me. In the transformer operation of the no load, if you have any doubt, you can ask me, else I will continue with the transformer on load. Okay. I will start the topic transformer during the load condition, or we can say that the operation of transformer on load condition. See, what is the difference between the previous case which we discussed just now and this case? There we have not connected any load on the secondary terminals of the transformer, isn't it? Yes. But in this case, we are discussing or we are analyzing the transformer operation during the load condition. So therefore, across the secondary terminals, there is a electrical load that have been connected. This rectangle, a small rectangle, this represents an electrical load which is connected across the secondary terminals of the transformer. Okay. So this is the primary, this is the transformer core, this is the primary winding, this is secondary winding. Across the secondary winding, we have connected a electrical load, and across the primary winding, we have connected the supply voltage which is connected across the primary winding of the transformer. Okay. Now, whenever you are applying an input voltage to the transformer primary winding, that is V1, it causes or it results in the current to flow through the primary winding, and that primary winding current which it is carrying is denoted with I1. This I1 which represents what? The amount of current flowing through the primary winding. This I1 current which in turn produce the magnetic flux in the transformer, and that flux what we are calling it as phi. Okay. So whenever this phi produced in the transformer, this result in producing the amount of EMF both in the primary winding as well as in the secondary winding. The amount of induced EMF in the primary winding produced is denoted with E1. E1 which represents the amount of induced voltage, statically induced EMF in the primary winding. E2 is nothing but the amount of induced voltage in the secondary winding. So this working flux which induce an EMF in the both primary and as well as the secondary winding. The amount of induced voltage in the primary is denoted with E1. The amount of induced voltage in the secondary is denoted with E2. Whether E1 is greater than E2 or E1 is less than E2, which completely depends upon the number of turns both on primary and as well as the secondary winding. The winding which having the more number of turns will have the more amount of induced EMF. As in the early classes which we already discussed, that is per turn. For one turn, what the amount of EMF induced in the primary, the same amount of EMF also induced in the secondary also. So the which side of the transformer will have the more number of turns, definitely that side we will have the more amount of induced EMF we will have. Suppose let us consider for 1000 number of turns, if you have the 1000 volts which induced in the primary winding, then for 100 number of turns in the secondary winding, what will be the induced EMF? It will be 100 volts only. So whichever the winding is having the more number of turns, that side we will have the highest level of voltage or more amount of induced voltage only. Okay. Okay. We will come to the topic again, transformer unload. So which induces an EMF both in primary and as well as the secondary windings, right? So this is secondary winding induced voltage E2, since it is connected through the load. Now it is start to supply the secondary current I2. Now it supplies the current to the load, and that current which is flowing through the load, which is called as load current or secondary current, that current which is denoted with I2. This I2 is nothing but secondary current, or we are also calling it as load current. Okay. So whenever this I2 current which it is flowing, okay, this due to this I2 current, there will be one more flux that will come into the picture, phi 2. Okay. Phi 2 is nothing but the amount of flux which is due to the load current flowing through the secondary terminals. This phi 2 which is equivalent to primary, if you represent it, then it is nothing but equals to phi 2 dash. Okay. So now in the primary winding, what will be the flux which we are going to be have? Phi 1, that is equal to phi 2 dash. Okay, plus phi 0. Hope it is clear to all of you. Any doubt from any student? Yes, I am again repeating. Whenever I2 current is flowing through the load terminals, which in turn produce the magnetic flux phi 2. Okay, this phi 2 with respect to primary, if you represent, then it is called as phi 1 dash. That phi 1 dash plus, due to the no load current in the primary, there will be a current, there will be a flux which is called as phi naught. That phi naught plus phi 1 dash, which is equal to phi 1. Okay, I will just give you the details in later. Okay, this phi 1 current which is only due to I1. Okay, and this phi 2 dash is nothing but it is a secondary flux with respect to primary it is. Okay. So now from the above circuit diagram, we can write N2 into I2 is equal to N1 into I2 dash. What is I2 dash here? I2 dash is nothing but the secondary current which represented in terms of primary. Okay. So N1 into I2 dash, that is equal to N1 into I1. Therefore, we can write I2 dash is equal to what we can write? N2 divided by N1 into I2. Therefore, I2 dash, which is going to be equals to what? What is N2 by N1 is equal to turns ratio. That turns ratio or transformation ratio. So that it is denoted with K. So I2 dash, which is going to be equals to K into I2. So this is a phasor diagram of the transformer during the load condition. These are the three vector diagrams we will get in the transformer operation during the load condition. Let me explain you one by one. So here we are discussing the transformer operation during the load condition. So the load the load which we are putting on the secondary terminals of the transformer are of three types. Either it is going to be a resistive load, or the inductive load, or the capacitive load. So based on the type of load which we are putting on the secondary terminals, the vector diagram which is going to be depends. Why? Because in the case of inductive load, the current which lag behind the voltage. In the case of resistive load, the current which is going to be in phase with the voltage. And in the case of capacitive load, the current which leads the voltage. So for the three different types of loadings which we are placing on the transformer, there will be three different vector diagrams that we are going to get. Okay, now let us discuss the phasor diagram for the three different loading conditions. Okay, so this is the vector diagram during the inductive load, this is the vector diagram during the resistive load, this is the vector diagram during the capacitive load. Okay, as we already know, always the primary voltage and the working flux phi, which is always working flux phi, which is always 90 degrees lag behind the supply voltage V1. So with respect to V1, the working flux phi which began behind the 90 degrees we will have. And if you draw the vectors I mu and as well as IW, vector addition of these I mu and IW, which nothing but gives the I naught. Here I have not represented for reducing the confusion. I just not represented I mu and IW. Directly I have drawn the I naught. In the previous diagram, how the I naught vector that we have, if you go through that, then we come to know how this I naught vector which we will have, it is with respect to phi, with some angle it is leading in value, right? So in the same manner I have represented I naught vector here, this vector which denotes this vector which denotes I naught. Okay, yes, this is the one which denotes I naught. And how the induced EMF in the primary and as well as secondary windings we will have. Excuse me, sorry. So this vectors which represents the induced voltage in the primary and secondary windings. Remember one thing, always the induced EMF in primary and secondary winding which are out of phase or which are 180 degrees with respect to V1, or we can say that the induced voltage in the primary and as well as secondary always directly opposes the supply voltage to satisfy the Lenz law. Okay, Lenz law, according to Lenz law, always the response which will opposes the cause of production, right? So for E1 and E2 cause of to produce, which one is the responsible? V1 is only the responsible one. So always E1 and E2 tries to nullify or try to oppose the supply voltage which is the cause of production. So that's why in the exact opposite direction to the V1 180 degrees we will get both E1 and as well as E2. Why I represented E2 is more magnitude while compared with the E1. If you go through this circuit diagram, it will be very clear to you. Okay, E2 having, I am considering E2 is having more number of turns, and that is why the reason here I represented E2 with the more magnitude while compared with the E1. That's it. Okay, that is the main reason. Now, as we already know, in the case of inductive load, always the current which lag behind the voltage by the angle phi, where phi is nothing but the power factor of the respective load which have been connected. So this is the I2 current which is lag behind the induced voltage E2 by an angle called as pi 2. This pi 2 which is nothing but called as the power factor of the load. Okay, so again I am repeating, the load current I2 which lag behind the induced voltage E1 and E2 by an angle called as pi 2. Okay, now this is secondary current with respect to primary. How can we represent? Exactly, for this one, if you draw the opposite phasor, then it will becomes I2 dash. In the circuit diagram also the same thing I have explained here. This is the secondary current I2. This I2 current with respect to primary, if you represent, then it is called as I2 dash. Okay. So this is the vector which is called as I2 dash. This is I0, right? So I0 and I2 dash, if you combine, then what we will get? The resultant vector which is nothing but called as the primary current I1. So this is the secondary current with respect to primary, secondary component with respect to primary, and this is the primary current. Addition of the primary no load current and as well as the secondary current, which resulting in gives the primary current called as I1. Which resulting in gives the value of current I1. Okay. So here this angle which is represented with phi naught, as already we know, with respect to V1, I naught current whichever it is having, that angle is represented with phi 1, and angle between V1 and I1 which is called as phi 1, angle between E2 or E1 with respect to I2 which is called as pi 2. This is the working operation of transformer during the inductive loads. This is the vector diagram which explains during the resistive loads. Okay. Yes. Now if you go through this, same here V1 and phi which are 90 degrees in degrees we have, right? And this is I naught current. Induced voltage E1 and E2 both are opposite to the V1, that is 180 degrees out of phase to the V1. So E1 and E2 these vectors. And since it is a resistive load, always the current and voltage which are in phase we will have. So this current which is in phase with the induced voltage E1 and E2. So in phase with means there will be no phase difference between voltage and current. So I2 which is in phase with the E1 and E2 we will have. Okay. So if this is the magnitude of I2, opposite to this exactly I2 dash we will get vector addition of I0 and as well as I2 dash, which results in gives the value of the vector which is called as I1. I1 is nothing but the primary voltage. Okay. Since it is a resistive load, there is no secondary power factor, that is the power factor is equal to 1. So therefore there will be no power factor angle here, and the angle between the V1 and I0 is called as phi naught, and the angle between this V1 and I1 which is called as pi 1. Okay. Now let me explain the operation of transformer during the capacitive load. So in the case of capacitance load, what will happen? The induced voltage E1 and E2 are lag behind the current, or we can say that current leads the voltage by an angle called as power factor angle pi 2. So in the case of inductive load, current lag behind the voltage. In the case of resistive load, current and voltage which are in phase. In the case of capacitive load, current lead the voltage by an angle called as pi 2. Okay. So if this is I2 means exact opposite to this I2 dash, we will get primary component of current, secondary component of current with respect to primary. Addition of this I2 dash and as well as I0, which resulting gives the value of primary current I1. Okay, this vector which is called as I1. So angle between V1 and I1 is equal to pi 1. Angle between V1 and I0 is nothing but phi 0. Angle between this E2 and I2 is nothing but called as pi 2. So this is about the vector diagrams, how we develop during the transformer on load condition, and this is the analysis which is carried out during the transformer on load condition. If you have any doubt, I will just stop the recording, and if you have any doubt, you can ask me.